Hello, my dear students. Now, this is the start of the third and the final portion of our Introduction to Communication course for Year 3 Computer After Prep 20ELEC09I. In the previous two portions of the course, we first make some sort of extrapolation or extension for our signals background, where we have learned where we deal with some extensions, let me say, to the signals course related to the properties of the signals, the Fourier transform, the system domain analysis, the filters, and all these. In the second portion, we go to the analog modulation. We first introduce the modulation as a general concept, and then we go into the main three types of analog modulation, including amplitude modulation, frequency modulation, and phase modulation. Now we are going into digitalization, where we are dealing with digital signals. If you remember, in the final part of the previous lecture, we have discussed together the advantages and disadvantages of the AM modulation over the FM modulation and vice versa. And we consider some key important parameter, which is the noise immunity, where we mentioned that the noise immunity for the frequency modulation techniques is much better than the amplitude modulation techniques, because in the frequency modulation, the message is contained in the frequency of the carrier. However, in the amplitude modulation, the message is included in the amplitude of the carrier. So for any imposed, so for any imposed noise, this will affect somehow the signal for the AM modulation. So now in the remaining part of the course, which is roughly about 4 lectures from week 8 to week 12, maybe somehow less, to be 3 lectures and 1 lecture revision. So in the coming 3 to 4 lectures, we are going into digitalization. We are going into the digital modulation of a signal. First, we are going to learn what is the advantage of going into digitalization and how we can digitalize our message. And then we will proceed into digital modulation techniques with different schemes related to shift schemes and quadrature amplitude modulation. So let's now have our first lecture in the third part, or totally lecture number 5, dealing with signal digitalization. Now I believe you can see my PowerPoint presentation, which is now lecture number 5, which is signal digitalization, and we can now start our lecture. Okay, so again, let's start with a flashback. In lecture number 2, where we deal with generally the concept of modulation, I show you this PowerPoint slide where we have an analog message. Normally, any physical quantity is an analog quantity, so temperature is an analog. My voice recorded is an analog. Images are analog. Generally, any data is in an analog format. Then we use any sort of a modulation technique, I mean here an analog modulation technique, in order to convert the analog baseband signal, if you remember, into a passband signal using what's called a carrier. This carrier is then transmitted over a channel, and then in the detector or in the demodulator, you are focusing to extract back the original message, or from other point of view, you are down converging the baseband signal, the passband signal, sorry, into a baseband signal, and then we are down converting the passband signal into a baseband signal. Then you can get your message. So this is typically what we did in the second portion of the course. We deal with the scratch shape, the scratch format of a message, which is an analog message. Now, in the next portion, what we are going to do is we are going to digitalize the message. So, as I mentioned in lecture number 2, we still have an analog carrier. So, when we go into a digital modulation, that doesn't mean that we digitalize the carrier. Actually, we are not going to digitalize the carrier. We will keep the carrier analog. However, the message will be digitalized to be a digital message. So the first step here, which is the first new interruption in the system with respect to the previous system, is the introduction to this analog to digital converter in order to input the message as an analog signal and to get the message as an output signal. Okay, so what we are going to discuss in this lecture in specific is how we can convert analog signal into a digital signal. But before going into this, actually we have to know what is an analog signal and what is a digital signal. So what is your input and what is your expected output? Herein, please accept my invitation to share with you my white paper and to start exploring the idea of analog and digital signals. So, generally, whenever we have a signal, this is t and this is x of t, whenever we have any signal like that, random signal, in the time domain, we call it an analog signal. That's true. However, we just need to frame this definition. So, an analog signal is a signal that is continuous in the time and in the amplitude axis. What I mean by continuous, if you search for any time value, you will find a corresponding value in time. If you search for any amplitude, you will find a corresponding value in the amplitude. So it's continuous in the x-axis, which is time, and it's also continuous in the y-axis, which is the amplitude of the signal or axis. Accordingly, we can say this is an analog signal. So, in order to perform what's called a digitalization, you need to convert these two continuous axes to be discrete. You need to make some sort of discretization in the time domain and also discretization in the amplitude axis. For example, if you have a signal looking like that, if you have a signal looking like that, and if I told you, yeah, is this a digital signal or an analog signal? Actually, the perfect answer is this is not a digital signal and this is not an analog signal. Actually, this is a semi-digital signal. Here, this signal is discrete in time. So, as you can see, the time values are only defined at certain time frames or time slots, which is 0, t2, t3, t, and so on. So, for example, at half t, you don't have a value for a signal. It's not defined. So, it's discrete among the x-axis, which is time axis. However, it's not discrete in the magnitude axis. At this amplitude can have any value. So the amplitude here is an analog. So this is a semi-analog signal. On the same manner, if I have a signal like that, again, this signal is discrete in the amplitude. You can see that the amplitude is only this, or this. So only it's limited only to 4 discrete values in the amplitude. However, the signal is continuous with respect to the time. So again, this is a semi-continuous signal, semi-digital signal. So this is actually very important in order to understand the overall process of sampling, of digitalization. That in digitalization, you are seeking for digitalize or discretize both the time axis and the amplitude axis. One of them is not enough. You have to do both in order to get a digital signal. By the end of the day, the digital format, based on your background as a genius digital engineers, is some sort of ones and zeros, which is a digital signal. So maybe the third step is how to convert it into the ones and zeros. Accordingly, if you return back to my PowerPoint presentation, we can define the digitalization process or the conversion from analog to digital into three main steps. The first step is what's called the sampling. In this step, we are interested in digitalizing or discretizing the time axis. I mean, converting the time axis from an analog continuous signal into a discrete digital signal. In the second step, we are interested in what's called the quantization process. In the quantization process, we are interested in converting the y-axis, which is the axis. I'm sorry for the discontinuity. Let me return back. So I believe now you can see my presentation. Okay, so let me repeat it again. I'm sorry. So we have three steps. The sampling step, where we are interested in digitalizing or discretizing the x-axis of a signal. In the quantization, we are interested in discretizing or digitalizing the y-axis or the axis of the signal. And finally, we need to convert this signal into ones and zeros, which is a typical known format for a digital signal. So this is what's called the encoding. So this is the three types, or the three, actually not types, I'm sorry. This is the three stages we are going to pass through in order to make what's called a signal digitalization or conversion from an analog signal to a digital signal. So let's start the journey further. And fortunately, we will start with sampling, where we are doing some sort of discretization in the y-axis. We need to discretize the y value, sorry, not the y-axis, the x-axis, the time domain axis. So let's start what's called sampling. So before going into sample, I will show you these two somehow boring slides related to the advantages and the disadvantages of the digital language. From my point of view, this will be something like some lines written in a boring way, but I believe that you will not observe this effect until you reach the next slide, which is the digital modulation. So for a while, let's believe, for a reason or another, that the digital modulation is or has a better immunity than the analog modulation. This is the main disadvantage. This is the top of the pyramid in the pros of the digital modulation over the analog modulation. However, of course, there is another list of advantages, but I will only focus on that, and maybe we will come to these advantages later on when we go during this lecture and the upcoming lectures. The main disadvantage is the bandwidth. Unfortunately, digital modulation needs larger, wider bandwidth than analog modulation. So again, there is another disadvantages. Maybe we will try to explore the advantages and disadvantages together while we are going through the lecture. But I'm just going to, or this was just in order to list the advantages or the disadvantages, and maybe in the end of the lecture, we will come into them one by one. Okay. So the first step is what's called digitalization or discretization of the time axis, which is simply the process of sampling. As you can see in this process, it's very simple. This dotted line represents the pure analog signal. It's an analog signal because this signal is continuous in both time and frequency, sorry, in both time and amplitude axis. Now I'm going to take some samples from this signal. So as you can see, this solid lines here represents the samples. I pick it up from the signal. So this is simply what we can call sampling, or between quotation, what's called an ideal sampling. So how can we perform such an interesting process? Actually, the answer is very easy. So let me return back here. running out of papers. Okay, so we have generally any analog signal. This is an analog signal. And I need to take some sort of a sample from this signal. So this is generally x of t. And of course, this is the t-axis. What I'm going to do, my dear student, is very simple. What I'm going to do is just multiplication process. So I'm going to multiply this with a series of delta Dirac function. Of course, they should be equally spaced, and my drawing is not so good, so they should be equally spaced. So we call this 0, for example, TS, 2TS, and so on, where TS is a sampling time. So by doing this multiplication, of course, all these delta Diracs has an amplitude of 1. So by doing this simple multiplication, what is going to do is that you will get something like that. Which is nearly, again, my drawing is not so good, so which is nearly the same shape of the signal. So this is simply what we do in the time domain. We multiply our sample, or our signal, our analog signal, with what's called a train of delta Dirac function. So what we get is simply this output signal. Okay, so the process of the sampling, again, I'm talking about an ideal sampling, and I will mention later on why this is an ideal process. So the process of ideal sampling is simply can be represented by a multiplication process between the signal x of t and a train of delta Dirac function, which is x delta of t, or we can call delta of t or whatever. This is just a train of delta Dirac function. Then you will get a discretized signal in the time domain. Again, don't forget, my dear student, this signal is not digital, still it's a semi-digital, because you have a discrete values in the x-axis. However, the values on the y-axis is still analog. So this is a semi-discrete signal. But let's go more and more into details related or concerning this signal, this interesting signal. And let's now start to study the Fourier transform or the frequency domain analysis of this process. So what I said is, this is just simply a multiplication process in the time domain between x of t and x delta of t, which is the train of delta Dirac function. Then you can get x, you can get x of n ts, which is only defined at 0 ts, 2 ts, 3 ts, and so on. This is simply the process. But we are now interested into demonstrating the process in time and frequency domain. We already did it for time. We already did it for the time domain. So we already have the knowledge of the time. So let's now divide the page into two regions. Here I will focus on the time, and here I will focus on into frequency. So let's start with the easiest one, which is the time domain. Generally, you have any message m of t. As you can see, it shouldn't be a periodic, any message, any random data. And now we have what's called the train of impulses. Okay. And then you have the discretized signal. So something like that. Let's turn to the frequency domain. Okay, so generally for this x of t, let's say that we have x of f with a bandwidth fm, of course, here this is negative fm. So generally this is any frequency signal. What about this delta Dirac? What about this train of delta Dirac? Actually, when I used to teach signal systems, I consider it as one of my tricky questions to my junior students. To tell you, please, determine the Fourier transform for this train of impulses. This is one of the examples that can demonstrate to what extent you understand the Fourier transform and its properties. So let's try doing it, and then I will return back to this slide later on, but I will just try to do the Fourier transform of a delta Dirac function. Okay, so what we have, my dear students, is something like that. So this is TS, 2TS, and so on. We don't know the Fourier transform for this delta train of impulses. We don't know. But if you turn back to my lecture number 1 slides in the Fourier transform, you know that whenever you have a delta Dirac function, its Fourier transform is a constant function. This is the Fourier transform. You find it, you can find it in my slide just after the example of the direct thing. Just after we have some a screenshot of some examples. This example was on the top right of the slide, if you remember. So this delta Dirac, well, you got a constant distance. Okay. Again, you know only one delta Dirac. Okay, what happened here? What is the difference between this and this? Remember my note, especially those students who are attending the extra sessions. Remember my note related to periodicity and discretity. The difference between this one and this one is that this is a single delta Dirac function. This is a single delta Dirac function. However, this is a periodic delta Dirac function. So what you did here is what's called the periodicity. You transfer a single period into a fully periodic signal. And as far as we know from our Fourier properties that periodicity in one domain cause discreticity in the other domain. Again, periodicity in one domain cause discreticity in the other domain. So, as far as you transfer this signal to be a periodic signal, this Fourier transform of this frequency domain will be discrete. Okay, then how we will discrete it? So just you will take sample of it. So it will become something like that. Can you imagine? This is a very, very unique signal where the format of the signal is the time and the frequency domain is identical. It's not 100% identical because this is a time domain where the spacing is TS, and this is a frequency domain where the spacing is FS, which is one of the TS. You can make it mathematically to prove it. However, the general format is identical. You have an identical format here and there. You have a train of delta Dirac function in the time, and you have a train of delta Dirac function in the frequency. Here are separated by time frame called TS or sampling time. Here they are separated by a frequency quantity, which is Fs, or the sampling frequency. So this is a very, very interesting structure. So now I can return back to my example where I have, this is the time domain and this is frequency domain. Now you know that if this is a train of impulse in the frequency domain, then automatically you will get another train of impulses in the time domain, in the frequency domain. But as you can understand that the time and frequency are reciprocal. So the closer the samples or the delta Diracs in the time, the wider in the frequency. Because now the distance here is Ts and the distance here is Fs, which is 1 over Ts. So as much as you get a closer delta Diracs in the time, the distances in the frequency will become wider. That's why I plot n delta Dirac in the frequency, in the time domain, and only 2 in the frequency. Now, in the time domain, we make what's called a multiplication process, which is automatically converted into a convolution process in the frequency domain. Okay, then what is a convolution? The convolution is very easy as far as one of the inputs as delta Dirac. If you remember, this is actually, or this is typically what we did with the carrier modulation. But I just forget that we have already have a sample or another one here because we have a delta Dirac and this and the z at 0, so we have a delta Dirac here. So now the convolution will leads to just shifting this message in the places where you have the delta Dirac. So what you are going to do, my dear student, is you will have a one triangle here, one triangle there, and the third triangle here. This is the output. This is the frequency domain. Again, discretity in domain because the periodicity in the other domain. Whenever you transfer your signal from an analog signal into a discrete signal, the Fourier transform is transferred from being a single period to be a complete period, which is typically what we do with the train of impulses. So this is very important in communications. So now you have 3 versions, or actually n version. It's a periodic signal. This period is Fs, so this is 0, Fs, 0, negative Fs, and so on. And this is actually the spectrum of the digitalized, or let me be more and more correct and say the semi-digitalized signal, because we did digitalization in the frequency, in the time axis, but we did not still did it in the y or the amplitude. So simply, let me now return to my slides. And let me open quickly the pointer. So simply, when we did this multiplication process with the train of impulses, what we got simply is that we got a multiple repetition of again, sorry for interruption. This is related to the quality of the internet, so I'm sorry for that. Let me share the presentation slides again, and let me also operate my pointer. So, sorry, so this is simply what happened. But do we have any sort of restriction for such a sampling process? What do you mean by restriction? Actually, what I mean by restriction is a restriction related to the values of a Ts and Fs. In order to understand me more, let me return back to my slides here. Okay, so you agree with me that the first period will come with Fs. And your signal is, here is Fm, and here is Fm. This value is Fs minus Fm, and this value is Fs plus Fm, and so on. What if, let me start. What if we increase Ts? What if we increase the value of Ts? Then automatically the values of Fs will be narrowed down because we agreed that time and frequency are reciprocals. So whenever you increase time, you decrease frequency. Okay, and then this triangle, will be go more and more closer to the main triangle. So what may happen is something like that. So let me do it here, for example. So this is the main triangle, the signal, and then you have the delta Dirac functions. For example, now they are closer because the sampling frequency is, sorry, the sampling time increase, which means sampling frequency decrease. So when you're going to plot them, you will plot something like that. And then something like that. Something like that. Okay. As you can see, these two triangles, or the spectrum of the signal, starts to overlap together. So the output, of course, will not be overlapped. The output will be something like the summation. So the output will be something like that. Okay. Your question now should be, what is the problem? Okay, they overlap. What is the problem? Okay, it's a very big problem. Why? Please don't forget that every step you did in the transmitter, you should do the reverse step in the receiver. So now in the transmitter, I convert the analog signal into a digital signal. So let's take an example. Let's assume that the analog signal is my voice. So the first step is you convert my voice into a digital signal so that you can transmit it over a digital modulator. Perfect. In the receiver, you need to operate this voice over a speaker. So you need to return back this digitalized signal into an analog signal back so you can hear it in your speaker. So you need to do the reverse process. Okay, so for this case, if I told you, please, my dear students, I need to convert back this digitalized signal into, again, an analog signal. You will tell me this is very easy. How? You will tell me we know that we have a smart device called a low-pass filter. So if I insert a low-pass filter with a frequency response like that, I will extract only the main triangle, which is the original signal, and I will kick out all other repetitions of the signal. So basically, you will return back to the original signal. Please remember the word smoothing filter. What you are doing now is you are smoothing your signal. You get right from this digitalized signal and you're smoothing your signal back. That's why we call the low-pass filter as a smoothing filter. So this is very easy as far as you still have a clean and clear main triangle and the passband. It's a passband because it's around zero frequency, by the way. But if overlapping starts to occur, or what we will call it technically a very important word, which is aliasing. So if aliasing, which is basically overlapping, if aliasing starts to occur, then if you use a passband filter, sorry, I'm not talking. If you use a low pass filter, what you will get is something like that. It's not the original message, because now the original message is destroyed, as you can see. So, in order to make an correct, appropriate sampling, you have to avoid this aliasing. Otherwise, you will not be able to restore back the signal to its original shape or format. So, how we can pick up the condition at which we can avoid it? So, it's very easy. Let's check this. In order to avoid aliasing, my dear students, you have to make the maximum of the baseband signal smaller than the minimum of the first harmonic. This value is FM. And this value is Fm plus Fs. So Fm should be all the time smaller than Fm plus Fs. So let's write it. Fm should be smaller than Fm plus Fs. I'm sorry. This is Fm, and this is Fs minus Fm. I'm sorry, this is Fs, so this is Fs minus Fm. I'm sorry. So Fm should be smaller than Fs minus Fm. I'm sorry. Fs minus Fm. Or basically, Fs should be greater than 2Fm. This is a very, very, very important sampling restriction, or what we call it the Nyquist sampling rate. Nyquist is a scientist. So the Nyquist rate saying that your sampling frequency should be at least double your maximum frequency in the signal. This is the maximum frequency, this is the sampling rate. This is a very, very important condition in order to avoid aliasing and to be able to restore back your signal in the demodulator or the receiver side. So, for example, if you are modulating my voice, and for example, if my voice extended, for example, up to 5 kilohertz, trivial example. So, if my voice extended to 5 kilohertz, in order to do a sampling of my voice, you need 10 kilo samples, or you need 10 times 10 power 3 samples per second in order to digitalize my voice. If you use a sampling frequency less than this value, you will not be able to restore back your original signal. This is very, very, very important to know for a sampling process. Okay, perfect. So let me now share my presentation again. And this is again typically what I did with you, my dear students. Here, this is Fm, and this is Fm, and this is Fs minus Fm. So Fs minus 2Fm should be greater than 0, or Fs should be greater than 2Fm, which is the Nyquist condition, if you remember. Okay. If you are concentrating on it, so this is actually the process, what we just described. So this is a repetition here, as you can see, and this is now he's using Fs equal typically 2Fm. So we can see that you have a shared border and tangential border, because Fm is typically aligned over Fs minus Fm. So this is the minimum sampling frequency you can perform. Otherwise, if you decrease the sampling frequency less than 2Fm, you will have an overlapping, or what's called the aliasing pool. Okay, so the next issue is, if you remember, starting from the first slide dealing with sampling, I told you that we are performing ideal sampling. Ideal sampling, actually, you will find it everywhere in the slides. Ideal sampling. So why is ideal sampling? It's ideal sampling very easy, because in order to perform this sampling, you need a train of impulses. That's true. And as you know, and I believe you already know, impulses is an hypothetical signal. Why? Because the definition of impulse mathematically, or the definition of the delta Dirac function mathematically, is a function with a zero width. Its width in the time axis or frequency axis is 0. And practically, it's impossible to create a delta Dirac function. It's impossible. So this model describes the conceptual part of the sampling. However, whenever you are doing a real sampling process, you can never generate a train of impulses. So you have to generate real signals with real bandwidths, which is not equals to 0. So this is very, Very interesting. Now, what we are going to do is we are going to turn into the real sample. Here we have made two types of sampling. What we call the natural sample and what we can call the flat top or sample and hold sampling. Actually, I will not go into deep details related to this part. I will just demonstrate the ideas. Maybe your colleagues in the other program in the electronics and communication have more and more time to consume with this sampling techniques. Here we are just demonstrating ideas because, as you know, it's a compressed one semester course, so we don't have enough time to go into details for each and every time. So in this case, as you can see, what we did simply is that we multiply our signal here with a train of pulses, not a train of delta graphs. These pulses have a width. So we got now this sampled version of the signal. Here, in this case, or in this manner, this impulse is very, or this pulse actually is very interesting for us. Let's now stop sharing for a while and check what is this impulse. So, okay, we need more paper. So, in the previous example where we did deal with what's called the ideal sample, we use a train of impulses, as you can see. And we prove that if this is x of t, and if this is ts, we prove that the Fourier transform for this is simply another train of impulses, but in the reciprocal domain. So whenever you have a narrowing down this ts, you will wide and vice versa. Now we say that this is actually hypothetical. This is not practical. This is ideal. What is practical is to generate a signal like that. This is what is practical. So this is the practical signal, or this is a practical that you can generate. It has a weight, for example. I don't know, I can pick it out from the slides because I didn't remember the value. So, okay, I believe they didn't mention the value. So it should be something very small, for example, tau or something like that. So this is, it has a real width instead of the zero width here. This is it has a real width. Now the question: what is the Fourier transform of this? This is very interesting. Again, another signals and system advanced question. What is the Fourier transform? So what we are going to do is typically the same that we did here. You know, one period. So if I have a one period of this pulse, this is typically the first Fourier transform exactly we did together. This is a rect function. So you know that this rect function will tends to be a sinc function. Again, you should ask me, why you make this sinc function too wide? This is simply because this tau is too small. And the first zero here, if you remember, is proportional to 1 over tau. Again, it's a reciprocal domain. So whenever you have a very narrow impulse or a very narrow pulse, you will get a thing which is more and more wide. Okay, great. Then, what is the next step? Periodicity in one domain cause discretity in the other domain. So simply the Fourier transform here is like that. So it's typically the same thing, but it's a discrete thing. So this is just an envelope. The samples are this one here, and this one there, and so on. So you have an envelope of sync with a discrete value, because this is now a periodic signal. So let me return back here to, yes, here. That's why when you observe now the profile of the sample signal, this is, as you can see, this is a sync function, and this is a discrete sync function. And now when you, this is, again, this is multiplication of the time domain, so this process is a convolution in frequency domain. So you get the convoluted signal again, you repeat the signal. Of course, the Nyquist theory is still applied. So the distance here, which is Fs, should be greater than double the frequency of the signal to avoid aliasing again. But now your sampled signal takes that shape or takes the profile of a sync function. As you can see, you have some sort of a weighting function due to the width of this delta curve. So this is actually the main difference. If you make a comparison between this slide and this slide, as you can see here you have a flat samples or flat periodic samples, because the width of this delta Dirac tends to 0. Whenever this width becomes somehow realistic, tau, you will get this shaped, sync-shaped profile, as you can see. So this is the first time what we call the natural sample. I'm sorry. I'm sorry for this confusion. So this is what's called the natural sample, as you can see here. So it's called the natural because the sample takes the shape of the signal from the bottom, from the top of the input, takes the shape of the signal. The other one, is called the flat top, or what's called the sample and hold. So you just get one value and then you hold all the period. You get one value and then you hold all the period, and so on. So we call it sample and hold, or we can call it also a flat top sample. And using the same procedure, also you can find out that Fourier transform, again, it's a sync shape, Fourier transform, so it's the same manner. And I will not ask you into details about this flat top, so this is just for your demonstration. However, you can follow the same procedure in order to understand the Fourier transform or the frequency domain analysis of this. So finally, in order to terminate this part of the lecture, we are going to deal with the recovery. We need to get back the sample, recover the sample. So as I mentioned, what you need is just a low-pass filter, or what's called the smoothing filter, so that you can pick up the main signal and kick out all other signals, as you can see. So in order to make this significant sample, you have to have what's called the sampling rate, otherwise you will have what's called the aliasing. Here this is the concept of aliasing, as you can see here, the aliasing concept, or the aliasing problem. We already discussed it before, I think. So what about, in order to avoid aliasing? This is very, very important slide. This will be our final slide, actually, in part number 1. So what about, or how to avoid this aliasing effect? Okay, you told me that we can avoid this aliasing effect by simply making the frequency of sampling double or more than double of the message frequency. However, I have to mention a very important point, that, for example, let me tell you, that for example here, this is actually too ideal, because you will never find a signal that have a certain frequency and after this, everything is equal to 0. Most of the time, you will find some higher harmonics here or higher harmonics there. This higher harmonics here or there may cause a very big problem, because whenever you have another version, this higher frequency can overlap with the message. So let me describe it somehow in a better manner. Okay, so ideally, the message has a frequency which looks like that. This is ideal. And this is FM, and this is negative FM. Okay, so whenever you have some sort of sampling with a frequency fs, so you will get something like that. And this third one here, and so on. Now you guarantee that fs is greater than 2fm, so you avoid aliasing. That's perfect. However, realistically, higher harmonics are always exist. Okay, so this is ideal. This is the ideal scenario. What if you have some unwanted harmonics here? Some over harmonics, some neither. Then, whenever you have a periodic signal, this will propagate here, but also this version will have its harmonics here and here. So the main version or the main period that will be extracted later on using a low-pass filter will be somehow affected by these harmonics from the right side and from the left side. So in order to be 100% sure that you don't have this aliasing problem due to any higher harmonics, we use what's called an anti-aliasing low-pass filter. So whenever you have a sampling process and you find a low-pass filter, let me go to yeah, and whenever you find a low-pass filter just before the sampling process, and I told you, please tell me what is the function of this filter, automatically it's an anti-aliasing filter. This anti-aliasing low-pass filter used to frame your signal to a certain bandwidth, which we call it generally FM, so that you can be 100% sure that no other harmonics now exist after the low-pass filter. So this anti-aliasing filter is very important whenever you are doing your sampling process. Now, this is the termination for part number 1. In part number 2, we are going to go through the other 2 steps. If you remember, we already did the sampling process. Now we are going to the other 2 steps, which are the quantization process and then the encoding process. I believe this will take much less time than the first one because the sampling is the most critical process, but I hope that you will enjoy it also, as well as I hope that you enjoy this sampling part. Thank you very much, my dear students, and see you in the part number 2 with lecture number 5. Thank you.